The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, welcome everyone to our seminar series about AI for Earth and Sustainability Science. I am temporarily replacing Gustavo for today because of the many train cancellations and delays that has been happening in the last days because of the flood in Valencia. But okay, in any case, I'm super happy to introduce Professor Christian Eigel today. Christian Eigel is a leading expert in international intelligence and remote sensing. He's currently based at the University of Copenhagen's Department of Computer Science with an academic foundation spanning from different institutions. Christian brings deep expertise in kernel methods, multi-objective optimization, and deep neural networks. He is a full professor and director of the Science AI Center. Christian is leading machine learning research with strong focus on advancing UN's Sustainable Development Goals. And today we have the privilege of hearing from Christian of some of the latest advancements in AI and machine learning. So please join me and welcome him. Looking forward to your talk. Christian, the floor is yours.
Thank you very much for the kind introduction. Thank you very much for having me. And yeah, thanks to everybody who found the time to tune in live and listen to my presentation. I understand, I mean, everyone who's interested in climate change mitigation, politics has something completely different on their mind today. So yeah, that's how it is. Let's go on. So what I would like to do to talk to you about today is about machine learning or deep learning methods for large-scale ecosystem monitoring. And in this talk, I will focus on work I've been involved in together with many colleagues here in Copenhagen, but all around the world. So I will try to give them credit by adding their names whenever they were involved. But yeah, so it's really my, I'm humbled that I have the honor to present all this where so many people were participating. So I'm a computer scientist, and I develop and analyze machine learning algorithms. And working at the university, this gives me the great opportunity to pick what to work on. And then it's, of course, nice to have the chance to say, okay, I work on AI and methods that in the end contribute to reaching the Sustainable Development Goals. That's, of course, a very broad goal, a very broad definition. And of course, we here don't work on everything. So this talk today focuses on two of the SDGs, namely life on land and related to that, climate action. So this is what I would like to talk about in this seminar. So first I will talk about tree monitoring, so because that's the ecosystem we are focusing on today. Then I will make a short detour and talk to you about monetary neural networks. So this is kind of a technicality, just to demonstrate how this work on remote sensing data also leads to research and new methods in machine learning. Then I will come back to the carbon stock development monitoring. And in the end, I will briefly touch on some new data sets we just released for those who would like to get engaged and also get their hands dirty and work with some data. So let's start with the tree monitoring. So why tree ecosystem monitoring? I think that it's kind of clear. So because tree-based ecosystems provide many ecosystem services, provide food, provide shelter. But what, of course, first comes to everybody's mind is that they considerably contribute to CO2 removal from the atmosphere. And because of that, it's central to many climate change mitigation strategies to include forests and to increase the number of trees. So many countries have committed to halting and reversing forest loss. So if you look, to back this up a little bit, I modified this image here from the IPCC. Where here in the top, you see 4 different models predicting how it could go in the future, looking at greenhouse gas emissions. And what you see here is that, for example, CO2 here for agriculture, forestry, and other land use, that currently it's actually a source of carbon. But the idea is that over time, it reduces to a sink. So this is something we have here in all 4 of these scenarios for limiting global warming, that we would turn our land use in a way that it becomes a carbon sink. So, and how should this be achieved? This you can see if you now look at the lower panel here. How do we have to change the land use to change the emissions as they are projected? So, and there you see a crucial role is to increase the amount of forests. So increase the square meters of forests we have. Now, what is the problem with these plans? So one is that, okay, one could argue that the focus on forests is a little bit limited because, as we will see, it neglects a huge amount of trees outside forests. And when just saying, oh, we need more forests, then the problem arises that there are many different definitions of what actually a forest is. So, for example, suddenly some countries declare that their tea plantations are suddenly forests. So, and which of course contribute much less to the positive ecoservices like biodiversity, carbon uptake, and so on, as, well, let's say a rainforest or something. So the other thing is that all agreements This is something what history tells us, are of little worth if there's no accurate, unbiased, and consistent verification scheme. So we need something to measure, actually, our tree ecosystems. Not only for checking all these pledges by the countries, but also if you think about the whole thing of carbon credits, right? So if people say, "Oh, let's plant some trees here," and then you can greenwash your activity or whatsoever, then we need a way to check that this really happened, that these trees were planted, that these trees survived. It's not only that these trees were planted there, but 50 meters from there, some trees were cut and so on, right? So all this carbon credit system can only work if you have a good reporting and measurement system. So against this background, my colleagues and I, we combine machine learning, remote sensing, and biophysical modeling for accurately monitoring and predicting ecosystem properties at a large scale. So this is just another slide how we envision our research to contribute in the future. So you see here at the top, in the red box, you see all different causes of tree and carbon loss, like deforestation, for example. And below you see ways to use tree ecosystems to improve the carbon balance. So just planting trees, forest restoration, protecting of forest areas, and so on. And in the middle, this is basically what we are concerned with. So we have satellite monitoring of the Earth, and from that, we can build up forest and tree inventories. We can quantify ecosystem properties. This could be not only the canopy cover, but this goes beyond estimating how much carbon is stored in a forest, perhaps estimation of the biodiversity, and so on. And this is then used to inform national authorities and stakeholders to take actions to mitigate tree and carbon losses and to invest in tree and carbon gain activities. So here's a video from a paper where we did a study in the northern part of Africa. So this is a zone investigation. So it's a dry zone, so it goes from 0 to 1,000 millimeter rainfall. So this is Sahara and sub-Saharan Africa. So where I'll go, of course, we tested this video before this presentation, and then it was working nicely. And now it kind of doesn't want to play along anymore. Okay, here the enemy, here it's back. So what you see here currently, these are 4 different zones measured as how much rainfall there is. And now this video should continue, but it doesn't. It's just not a good day today. Well, okay, let's try to click through it. That's of course a pity. It's just symbolizing here. Sorry that this video is not working. So that's That's irritating. So we tested. So, but this is how things go. So so we go into high resolution recordings with a sub-meter resolution, which allows us to identify trees, individual trees. So, and after that, we can then use heuristics to infer from the tree crown sizes how much carbon this particular tree stores. So in this particular study, we actually looked at almost 10 billion trees and covering an area about 9.6 million square kilometers. Clearly something a human cannot do, right? So you need to automate this. So yeah, so this is a summary of what I just said. So there's a viewer where you can go in and check out our tree map and visit every individual tree in Northern Africa. The color code here is an estimation of how much biomass or carbon we think this tree may store. And yes, also one thing to be perhaps aware of is in this, we trained this on non-public high-resolution data, but visualize on a different satellite imaging source. So therefore, if you see some misalignments in this maps, this is mainly due to that. So how did we do that? So we used deep learning for that. So we trained neural networks to identify the trees in the satellite imagery. Concretely, my colleagues labeled almost 90,000 trees by hand. That served as an input to teach a neural network to distinguish between trees and other objects in the images. We use so-called deep neural networks, convolutional neural networks. I think this is a technology many of you will be familiar with. So most of these studies are done using some kind of U-net architecture. So because you can depict it like this, so that it resembles the U. So here's the input image coming in, some satellite or aerial remote sensing image. And then depending on the task, this image is processed, and then we have different outputs. So this could be a pixel level classification, masking all the tree crowns. It could be an object detection, finding all trees. We could also have a system where we just predict where a tree is and not segment its canopy cover. This makes labeling more easy, so you need not delineate every tree, or just point at it and say, okay, there's this object, there's a tree, and so on. Or we have outputs which quantify the whole image patch that has been presented to the network, which are just predicting the total biomass or total tree count. So these neural network architectures, they differ a little bit depending on the application, but they're basically they're based on the standard convolutional neural network ingredients as convolution, pooling, and so on. So I just use this slide here. Don't want to go into the details. So these are just the standard deep learning ingredients. So just perhaps advertising that there is a review paper out coming in January, I guess, where this is a little bit explained in more detail. So, but we can, the question is, okay, if you can do it for North Africa, can you not scale it up to the full continent? And yes, that's possible. So this is a study where we worked on a little bit lower resolution data. So we have 3-meter resolution here, and looked at the whole continent of Africa. These data, from these data, we labeled 130,000 trees, and then ran our algorithm on the whole continent. And here you see how diverse the scenarios can be. You have agroforestry, isolated trees, but of course you have also rainforest. There, in this application, we did not separate between the individual trees, but just measured the tree cover there. And interestingly, we found that 30% of the tree cover was found outside areas previously classified as tree cover. So if you would just base your analysis on low-resolution, outdated forest maps or traditional forest maps, let's put it that way, that do not consider trees outside forests, you basically miss almost 1/3 of the tree covered area, the tree crown covered area. Yes, so now let me dive into one technical issue here for those people who are into AI. And sometimes I get this question, okay, this is not from a machine learning AI researcher perspective. This all sounds very, very applied. So is there also some kind of machine learning research in this? And yes, it is. There are a lot of technical challenges that push us as machine learning researchers to develop new techniques and also bring the field of AI and machine learning forward. And I'll just give you now it's not very egocentric, narrow thing, just to give you one example here. So I already told you that we kind of estimate how much carbon there is in a tree based on the tree crown. So that already is, of course, from this is already clear that this can only be a very rough estimate, right? So because typically if you would say, okay, what do I need to know to estimate how much biomass or carbon is in the tree? So I think the first things that come to your mind is how high the tree is and what the stem diameter is. So these are the most important things. But in this case, we have to work with what we have. And as we don't have the height, we just work with the tree crown. And there you can establish relations, how this is related to the biomass based on very basic allometric equations of these kind of power law equations here. So where y would be, in this case, the biomass or carbon, x is a tree crown. And then these coefficients here are estimated from some data. So, and the natural question is, okay, this is a super simple model, and therefore it's most likely very, very wrong. And if we have data, can we not learn a more accurate model of how we can get from tree crown size to biomass? And as a machine learning researcher, you then think, okay, let's learn this relation using some statistical model, in this case, for a neural network. So you see to the right, these points here indicate how the wood dry mass, so the wood biomass in the stem, basically, scales with the crown area of trees in the area of interest. You see it's quite a messy plot from the data science point of view. And we would now approximate this by a function that approximates kind of the mean behavior. So what is the mean biomass we can expect given a certain crown area? So in an expectation, so what can we guess there? And so now we can fit a function through these points. So this is what the machine learning guys do, right? So however, we have a clear constraint here, namely that we would like to have this function to be monotonically increasing. That makes totally sense, right? So you would not accept a function which suddenly has a bump saying, so okay, the tree crown gets bigger and then the biomass gets smaller. While this can of course be true for individual traits here in something that just models our expectation, that's not acceptable, right? So, and of course there are methods which do so. So here in the plot to the right, you can, for example, fit the popular method XGBoost to it. That's a tree-based method, which you can actually ask to make a non-decreasing fit to these data, and then you get a model like the green one here, which actually fits the data nicely. However, it looks not very plausible from the natural science point of view, right? So it's not smooth, has this piecewise constant. It does not really extrapolate here as you would expect if you go to higher crown areas and so on. Or you can use a monotonic neural network to learn this relationship. So the orange line, this is what a so-called min-max network would give you. And that notoriously underfits the data. So that's actually a model which has very nice theoretical properties, but in practice you get typically results like this. So in this case, it's basically just a linear function approximating the data. Because of these bad results, actually, that this min-max neural network became out of fashion, although it's actually otherwise very nice and has nice theoretical properties. So this is what I basically said. So these models should be non-decreasing, if they predict biomass based on tree crown area, height, stem diameter, and so on. So because of that, we are interested in these partially monotonic statistical models. But these have also other applications. So first of all, they can incorporate any other type of physical knowledge. So in this case, we incorporate biophysical knowledge. That should be an increasing function. But it's also important in completely different contexts to implement ethical principles and social norms, such as favor the less fortunate and do not penalize good attributes. So this means that if for some reason you would like to use an artificial neural network or machine learning system to make a decision about a person, and then you have two persons which are completely equal, except in one attribute, where one person is clearly better in relation to the task, then of course this person should also be favored, right? So it should not be the other way around. And things like this can be enforced if you use a system which can only be monotonic in that particular attribute. So therefore, we developed a new system which is actually based on this monotonic min-max network. So, which, for example, can fit the data as this red line here. The new model is called the SMN, the smooth min-max network, which I would like to briefly motivate here. So this is the seminal min-max neural network architecture as proposed by Sill in the last century. So it's an architecture like this. You have K groups, 1, 2, 3, in this case, of linear neurons. So these are these round things here. So they just compute an affine linear map. And you have K groups of those, each containing a certain number of neurons. Let's say also K, just for simplicity. So here you have K groups, and each one of those has K linear neurons. Then you feed them into a max operation, and these max operations are then combined by a minimum operation. Then you additionally demand that the weights of these linear neurons here are all non-negative or positive, which then means that these functions are monotone increasing. Max and min are also monotone increasing. And this combination then gives you in the end a monotone increasing function. And because max and min have the property of being either convex or concave, you have basically the combination of convexity of convex functions and concave functions, which allows you then to approximate any monotonic function arbitrarily well. You can actually prove that if you just have, on a very mild constraint, if you just have a network of this type which is big enough, then you can arbitrarily well approximate any monotonic function on a compact domain. So typically asymptotic approximation results. So super nice, and I think pretty elegant. However, they do not work well in practice. So, and therefore, a lot of, I would say, rather complicated and often compute-intensive alternatives have been proposed. So if you go into the machine learning conference over the last years, you always find papers on different things, how to enforce monotonicity of neural networks. So and we sat down and asked ourselves, okay, why? Let's go back and let's think of why do they not work well? And the reason why they not work well is that the training doesn't work. It gets stuck. And why does it get stuck? Because the derivatives vanish. The reason is you have this max operation or min operations here, and they are, of course, they look kind of like this. If this is a function of x here and c is the constant, so until this constant c here is reached, the derivative is 0, right? And then if the argument gets larger than c, then you have this linear behavior and you have a proper non-trivial gradient, right? So, and then therefore, these neural networks, and you can show this empirically, they just get stuck and they have a lot of dead neurons. So dead neurons means they never participate in the computation of the output because they're basically set to 0. And they also don't move during training because the gradients are 0 and they do not change. So once you've realized that, then it's actually almost straightforward to come up with a remedy. So you then replace the function min and max by a function that always has a gradient. So you use a smooth approximation of it. You cannot use any smooth min-max function. You would like to have one which is strictly increasing. So this is provided actually by the log sum x function, which you see here. And now the idea is to replace the min and max by the corresponding soft min and max, which is based on this log sum x function here. So what do we then get? So first, we inherit the nice theoretical approximation property, so which I outlined here. So the corresponding architecture can still approximate any function arbitrarily well. So it's actually trivial to prove, almost trivial to prove that. So you have an architecture that can be trained end to end. It's simple, very computational efficient. It learns smooth function, and it also compares rather well to the typically much more complicated approaches compared in the literature. And this is now something which finds several applications in our work, for example, to learn allometric equations, but also to learn monotone image transformations of remote sensing images, and so on. So that I gave just as an example where certain tasks in machine learning for remote sensing triggers machine learning research. But now let's come back to the main topic of the talk and to ecosystem monitoring. I would like to give some positive examples here. I mean, today is a good day to talk also about some positive things. So this is these images in Senegal, and here we're looking at the agroforestry. So combining agricultural land use with trees. And by having our monitoring in place, we can, for example, find out that in this case, we see an increase in the number of trees and also the carbon stored in this area when looking from 2002 to 2021. So the color code of these squares here indicates is a measure of how much carbon there is in that area. The lighter, the more carbon, and you see the whole image gets brighter from the left to the right, which is a good sign in this case. So we think that the technology has reached the stage where we can say, okay, we have now something which allows, in theory, to regularly monitor trees globally over time to explore their role in climate change mitigation, loss of biodiversity, and so on. To show how this can actually be used to influence politics and lead to action, I would like to talk a little bit about the following study headed by my colleague Maurice. So he worked on the country Rwanda. Rwanda is it's not a super large country, but it's very interesting. It has a very diverse nature, very diverse landscape. So from the tree point of view, you have agroforestry, shrublands, urban tree ecosystems, plantations, and but you also have rainforests there. So and hey, so he set out and tried to delineate every tree there and counted all the trees. And well, I mean, this always means that of course we can miss a tree every now and then. But the principle is that we have a method which can detect individual tree crowns in principle and tries to count them as accurately as possible. There are of course obvious limitations. When we talk about forests, we of course only see the overstory trees, or the understory trees we don't see, right? That's that I would like to stress. And if we look at very dense canopy cover, like here in the first column, then it's often even for a human super difficult to distinguish where one tree stops and one tree ends, right? So in there, there's a lot of heuristics involved to split individual trees in these classifications, but they work pretty well, but of course are only approximations, right? So then we apply different allometric equations to estimate the tree biomass from that. So we use different allometric equations depending on the tree type and whether it was in a forest or whether it's a plantation, right? So not really. So we're not yet really differentiating every single species of trees and then apply an allometric equation that's tailored toward that. But we make rough distinctions between different scenarios. And this now allows us to turn this into some recommendations or at least input for policymaking. So my colleagues developed based on that different scenarios how agroforestry and forest restoration can help Rwanda to reach their goal of being carbon neutral by 2050. And there are different scenarios because now for example, we can say, so what is the potential of agroforestry? So what is the tree density in agroforestry areas? What is the maximum tree density? How reasonable is it to plant more trees there? Or what is the density in trees in forests that could be that are degraded? And what is the potential of really doing restoration efforts there? And based on this, you can come up with recommendations where to invest money and what the potential benefits in these areas are. So, and here indeed it comes out that if the emission levels remain constant, then agroforestry and restoration of degraded national forests could offset about 80% of the natural emissions of Rwanda by 2050. Here you see a mapping of change. So it turned out that Rwanda smallholder farmers on average planted about 3 trees per farm from 2008 to 2019. Here you see some examples. Here in the top, you see where this is located. And again, here below, you see this map where, again, lighter means more carbon stored in that area. Right? So we can really then quantify and see, okay, more than 50 million new trees actually were planted between 2008 and 2019. So we have basically a methodology at hand that allows us to quantify the progress and the impact of landscape restoration projects, and again, can then lead to policy recommendations. So Finally, I would like to talk a little bit about different modalities. So far, we talked about the analysis of 2D data, 2D satellite images, but this has some limitations. One important one I already mentioned, namely that we can only see the overstory trees, and we don't have any idea about the tree structure. It's also difficult to estimate tree height from 2D images. This is possible, but it would of course be nice to directly have some 3D information. And this can be provided by 3D LiDAR point clouds. So only very briefly, I would like to highlight one recent study in Denmark, where we have airborne LiDAR data of very high quality. And where we combined these data with very accurate measurements from the National Forest Inventory, where they had certain plots of forest, where they actually went out, made field studies, quantified the carbon stored there. We matched the corresponding point clouds, and then used a particular neural network, which is now specialized on processing 3D point clouds, and then directly regressed from the point cloud data to biomass. And we're currently working on a Denmark-wide biomass map using this technique, because it turns out that this is more accurate than the techniques that have been in place so far, which are then typically just doing some very, very basic spatial statistics of the point clouds and use this for biomass estimation. But of course, not every country has a dense coverage of LiDAR data of the forests. However, what does exist is LiDAR data from satellites, and the known mission here is the JEDI mission. So this is a satellite which produces LiDAR measurements. So this is shown here. If you go to this panel here in the middle, lower middle, then you see that for certain footprint patches, you get these full wave forms here that are kind of a height profile. And from this, we can not only estimate the height of the trees, but we also would like to know something about the understory trees and the biodiversity. And I personally think that this would add a lot of additional information. We are currently bringing this together based on my work for my colleague Nico, together with Sentinel-2 optical data, combine it so that we can also extrapolate a little bit from the JEDI information, because JEDI currently has not a dense coverage of the whole world, but these are rather patchy measurements. And to interpolate between those, we use, again, a deep learning-based approach to then estimate these height profiles from areas where we don't have JEDI measurements. So this brings me to the last point of this talk. This is where I would like to advertise some data sets we just released. And just for those who think, okay, that sounds interesting, so I'm working on machine learning, I'm working on deep learning, I would like to have some already processed imaging data to play with. So the first data set I would like to present to you is what we call the Nakala roof material data set. So here we leave the territory of trees and look at man-made objects, namely houses and their roofs. And this data set is interesting and part of a project which deals with malaria risk estimation, or more general with the estimation of the risk of being infected by a vector-borne disease. And there it has been shown that the risk of malaria is actually related to the properties of the housing, and in particular related to the roof material. So the infection risk is or the risk of being bitten, and then therefore the infection risk is higher than you have a traditional thatch roof compared to a metal roof, for example. So therefore we have here a data set. This is drone data, where we have segmented all the buildings and additionally classified what kind of roof material it is. So if you're into object detection and subsequent classification, that is perhaps a data set for you. Very, very high resolution, below 5 centimeters. And finally, I would like to point out the Earth dataset. This is a dataset we compiled with the goal to provide data for people who would like to build foundation models for remote sensing data. So we have a global dataset for geospatial representation learning. So we have 12 million locations uniformly sampled over biomes. So we have a little bit, so we are mostly interested in this natural task. So we really wanted to have all different biomes well represented. And then for every of these positions, we have 12 different modalities. So these modalities are a Sentinel 2 10-meter resolution image. These are the position. This is the land cover map at that area, the canopy height, what kind of ecoregion that is, what biome that is, when the image was taken, and so on. So there are 12 different, this is illustrated here a little bit in this, here to the right. So there are 12 different modalities associated with each data point. And as an example of what you can do with it, we trained a foundation type model, or several actually, with these data, which takes Sentinel images, Sentinel satellite images as an input, and then tries to solve all the remaining 11 tasks simultaneously. So you take the image as an input, and then you should reconstruct it first, and then you have also the 11 other tasks like predict where it is, predict the biome, predict the land cover, predict the canopy height, and so on, right? So with this, we actually would like to learn a representation that is for these kind of ecologically relevant tasks rich enough so that then now people who have another ecological application, but only very, very limited training data, can use these foundation models as a basis, and then by fine-tuning them or by linearly probing them, get a classifier or a regressor for their task very, very cheaply and with very, very little data. So we see there a big advantage compared to other foundation models. I mean, there are a lot of them who came out recently, is actually that we not just want a representation which is good for reconstructing the image or for learning land cover, but many more other what we think are relevant downstream pretext tasks. So so you can download these models, but in particular the Earth dataset, if you like. So with this, I would like to conclude this talk. So I would like to encourage you to apply AI for remote sensing data. I think we made a big progress over the last years. So both because there's better and better higher resolution remote sensing data available, but also we have now the AI, machine learning, computer vision methods in place to exploit these data. So the time is right to bring these things together and do something good with it. There were some topics I haven't talked about so much, but which I think will be important in the future. So I gave this this neural network architecture, this monotone neural network architecture may be going in this direction, but one important thing for the future will be to have a better, to work more on integrating machine learning and AI models, and here it's called mechanistic models, but biophysical, biochemical models. So how can we use all the scientific information we have about, for example, greenhouse gas fluxes? How can we bring this together with data-driven approaches to get the best of both worlds? So that's a topic that comes up all the time. So if you're looking for a nice area to work on, so I think that's super interesting. And the other thing is uncertainty quantification. So getting, for all these predictions and estimations, proper error bars that are really trustworthy is, of course, important here. And it's important across the national sciences, but here we have really something that we think, okay, this should be used by policymakers to make the decisions. Then we really have to be sure about what kind of information we provide. So this brings me to the overall message of this talk, which fits this seminar series. So let's work on AI systems that help to reach the SDGs. And yeah, so that was it for me today. I'm happy to answer any questions regarding these works. I would like to thank my co-workers or my collaborators who participated to this great research. So it's really interdisciplinary. You have a lot of experts from the geosciences, from ecology, people doing the field work, which is important to ground all these approaches, and if statisticians, machine learning people, and so on. It's really a pleasure to work with all these great people. And yeah, I'm very happy that I had the opportunity to present our joint work. Thank you very much.
Thank you so much, Christian, for this super interesting and comprehensive talk. I think it's really, really cool stuff. And yeah, I imagine that this massive work has required a lot of effort, and yeah, the number of co-authors and collaboration is also huge. So yeah, thanks. And yeah, I have a couple of questions. Maybe I can start with, there are other questions also here in the chat, but I will start first. It's kind of general, but if you could ask for a wish to improve your modeling approach, what would you ask for? What would you prefer? Better satellite information, more computing resources, or better ground truth data? So what's the most limiting factor? It's kind of embedded, that question, at some point. Oh, so I think you are muted, Christian. Christian, you are muted. Sorry.
Okay, so the good question. So I would say that the least important one are the compute resources. So we are, of course, always would be happy to have more of those, but this is something where we think, okay, for this we will find a solution, and the model is also not so big, so that's not an issue for which I would burn a wish. I wish for more compute resources, but I don't need some miracle here. So what was the other thing was, of course, the ground truth data.
Yeah, and better sensors.
That is it, I would say. So because that is so the satellite data, I also think this will also kind of automatically come. So satellites data just get better, the coverage will be better. So this is also something which is for us not easy to come by. So some of the studies I presented are actually based on commercial satellite data, where we had the pleasure, because of collaborations, but to work with, and also where we paid money to buy these data. This is therefore also a problem, but perhaps also not a problem for which I would waste a wish for the genie. That I would then rather say it's the ground truth data. That is, I mean, that's the most difficult thing to come by In particular, so we would like now, getting better biomass estimates, then we need a lot of more ground truth about the biomass. Biodiversity, that gets tricky. So it's something we are currently working on. And there, of course, the data is very limited, right? So how do you measure biomass actually? And how can you compare this? You, of course, have studies who then quantify biomass for rather limited areas. And how do you compare their assessment of biomass across different regions and stuff like this? For this, we need a lot of field work and ground truth data. So my long answer to this nice question is, for my wish, I would wish for more ground truth data.
Yeah, probably also one of the most expensive ones, right? Because it's so difficult to record. Now you need to send people to the ground and so on. Yeah.
Yeah, it needs to be experts. Yeah.
Exactly. Yeah. So I think another question I had, or a comment, it's a question. I guess it's related also with the fact that maybe growth through data and it's related with uncertainty, as you mentioned also at the end of your talk. Is have you considered any transfer learning strategies in order to be able to run your predictions in other areas or even in other time periods, just to being able to assess or to know you can apply this to other areas?
Yes. So I would argue that the MMR thing would be an example of transfer learning, right? So this is basically here's the idea. So this kind of a baseline pre-trained, that the models are pre-trained neural networks. And then we hope that this representation learned here transfers to many different tasks. And that's actually the feature that we train a representation already on 12 different tasks, so that we hope that it's has enough information in it to then also be transferred to other exciting problems. So that's the idea. Yes. So the answer is yes. So that's the way around. So, for example, if you have then very limited biodiversity data of an area, which is not enough to train a full neural network architecture, then you can perhaps start from using LMRs on Sentinel, which is freely available. Yes, that's the idea.
Thank you so much. Yeah. And the people really got super interested. There are a lot, but not lots, but yeah, there are some questions here for you. I don't know if you're able to read them, but I'm going to read them for you. So there is a question here from Nima Kamali. She said, did you use same level data for the whole continent prediction as well?
Could you please repeat again the question?
Did you use same level labeled data for the whole continent predictions as well? Yeah, I guess if you have used the same data for the whole continent.
No, it was not the same data. So no. Therefore, which we labeled again. So my colleagues, this is really a lot of effort goes into this labeling more than 100,000 trees in that case. So simply because the resolution was different. So it was different imaging sources for different satellites, Maxa versus Planet for the remote sensing experts in the audience, and for this we labeled new. Yes.
Okay.
So
I think
yeah.
I think you already answered this question, but I'm going to tell you again. Is Asonima asked, how did you map the tree images and carbon biomass? How do you realize the biomass of each tree? I guess that's this prediction.
So again, yeah. Well, that's a good question. So currently, what we're doing is that we measure the properties of the trees, whatever we can get out. In this study I presented, it's basically just the size of the canopy. So how big does the tree look from above? And then we have data from that area where this tree is. So where there were real field measurements of canopy size and carbon. And then based on this, we learn this functional relationship. Can I show this again? Quickly or run back. Right, we learn a functional relationship like this, And then we look, okay, it's 40 square meters, and then we take this value for that. And then we, of course, if we distinguish a little bit between, if, for example, if you say, okay, this is the plantation, then we need use different equations for that than if it's a forest, a rainforest, for example. But that is clearly where there's a lot to gain by, I mean, ideally you would find out combining this with height estimates and trying to estimate what species that is. So the more information we have, the more accurate the estimation will be. That is the biggest source of uncertainty in these biomass maps we are presenting. It's not the finding of the trees. There are also errors, of course. We miss trees or mislabel some, right? But that's not that works very, very robustly. It's really then translating this to biomass. This is very heuristic. But of course, I would say it's a completely different level of granularity and accuracy than there was before these types of studies, where you basically had coarse resolution forest maps. Oh, this is kind of a forest, and then you just estimate just on the square meters of that forest how much biomass this will be. So I'm very happy about the progress we made. I think our estimates are much better than there was before, but still they are very noisy. So, and then, of course, it's a field study is much more accurate, and there's a long way to go to reach the accuracy of a real field study. So there's still, it's not everything is solved, and we are working on it.
Yeah. Okay, another question. Thanks so far. This is another question from Carola Portuno, and she asked, is it possible to measure that some tree species absorb more CO2 than others?
So first, so just ask like that. Yes, of course, a lot of biologists and scientists do studies like this. I mean, you can experimentally, of course, measure the CO2 uptake of different species. Yes. So I don't know whether the question was whether we can see it from satellites.
Yeah, I guess it should be related. Yeah, I guess
Yeah. So
she's referring to your maps. Yeah.
So I put it that way. So our current strategy is to say, okay, we do real experiments. So my approach is we do real experiments. So we figure out, so what is the greenhouse gas balance of a particular tree species, and then we try to figure out, can we detect this tree species from remote, and then bring these two things together. That would be my approach to that. And yeah, so because measuring greenhouse gases from remote is super difficult. I mean, also because because just you then have to take the whole height of the atmosphere into account, and then the things blows. There's wind, atmospheric changes where it goes. It's tricky. So it's actually something we are interested in. So this is also for other greenhouse gas things. So for example, very interested in methane emissions from wetlands and stuff like this. So we're trying to go there, but that's really difficult. So here for trees, because the trees are nice, they don't move so much. So there I would rather think, let's detect trees, try to figure out how high they are, what species they are, and then look up, okay, a tree of that type and height has this and this expected greenhouse gas fluxes. So this is how I would go about it. For other areas, like for example, for wetlands, we are trying to estimate this from remote sensing. So, but that's ongoing research.
Okay, thank you. Let's continue. There are some other questions here. Lots of interest. That's super nice. So Ingo Fetzer asked, following thing, I guess that tree monitoring is very region specific as tree species composition varies strong between regions, and with this, the carbon storage capacity. Have you done any estimate of how region specific your machine learning trainings are?
Yeah, yes. I mean, that's totally true. And so therefore, as also briefly mentioned before, so these are very often, while the technology is the same, these are different models, right? So we have different models if we have different satellite imagery, different resolutions, but also for different regions. I mean, the most comprehensive one is so we have one for Europe, which covers the different settings in Europe. Then the one for Rwanda, which covers the full country, then the one for Africa. So, but yes, they are very country specific. So, of course, the one we trained on Northern Africa drylands, if you apply this in Europe or apply it to a rainforest, it will just give crazy nonsense results, right? So, as always in machine learning, you have to train a model with data that is representative of the data it will later see when it's evaluated. Otherwise, you will get not good generalization, right? So at least you cannot typically not expect that. So yeah, so it's very region specific. Also, these what kind of species they are, of course, influences how much carbon there is stored, and all this is region specific. So, but I'm super optimistic. Well, I'm not only optimistic. I'm actually sure. I clearly think it's not a problem to have a model for the whole world, where we then would have perhaps different machine learning models depending on the region. So one for Europe, or perhaps one for Northern Europe, one for Southern Europe, several ones for Africa, perhaps, and so on. So yeah, theoretically, this could also be combined in one super big machine learning model. That may also be an option, but it's not necessary. So I don't see the need why one should do that. But this one could do. So I hope that this answers the question a little bit. So, but you're totally right. All this has always to take the region into account, and we see some very, without naming, you see sometimes very bad global maps that are released, which were only trained on very local data, and it works very much nicely in that area, but in all the other areas they look not good. I mean, that's a very known phenomenon, and one has to be very, very careful not to do this.
Okay, thank you. There is another question. I think you actually responded a little bit that before, but Bikash Kodati asks, well, thank you for the session. And the question is there a paper or article on the current state of machine learning models in this space?
So there's a very good article by Reichstein and others on the role of deep learning in the geosciences and remote sensing in general, which appeared in Nature some years ago, which I still think is a very good introduction to giving an overview of where different things where machine learning can be used, and that area. This I still recommend. So I think that's a good one. And then for concretely this work on tree ecosystem monitoring, if you look at this slide on the lower right, so this is now some shameless self-advertisement here. So we have a review article that comes up very, very soon. It's in press, and I don't know, it will be released later this month or early January. And from which, for example, this image here or the neural network images are taken, which should give hopefully a good introduction to the field. And from this, you can then move to the individual studies.
Thank you for that question. Also, there is a couple more specific questions, and those are the last ones so far. So, Eldad Agui Bekoe asked the following question: is it possible to obtain data sets that covers, for example, cocoa plants in Ghana? That is, with the aim of monitor cocoa ecosystems in Ghana. I guess there is like some specific maps for that.
Yeah. Nice question. I cannot. I don't know. Honestly, I don't know. I mean, there are for Africa there are some older high resolution data which can be obtained. You can of course get lower resolution 10-meter resolution sentinel data from the area. Whether you can get cacao vegetation maps, I don't know. It could very well be, but I cannot answer this. But you could reach out to one of my colleagues from the geosciences. They have all this insane knowledge that, okay, for this area there's this data exists and so on. So I cannot answer. So it could well be whether cacao is. I know that there are studies out who looked at that, but I don't know in which country. I actually don't even know which continent, I have to admit. So there's a little work out there, or there's some work out there, but I don't know whether the data is freely available and what input source they used.
Okay, thank you. So there is another question, but I think that this is two more questions, and we probably will be close. It's Kumut Khan asked the following question: can you please explain how material of roof can determine the vector-borne diseases?
Okay, yeah, good question. So I can. So if you write me, I send you the paper showing that. So I'm not a super expert in this. To my layman understanding, there are several reasons for that. So the first one is that the metal roofs cannot so easily be penetrated by vectors. That's one. And the other thing is also that, which actually typically we'll think it's a bad thing about metal roofs, but the inside room temperature increases. So I mean, that's actually a good thing to have a thatch roof, that you have more ventilation and stuff like this. So it gets warmer inside, which is of course not good. However, the mosquitoes also hate it. So to my limited understanding is that the increased room temperature is another reason why the mosquitoes stay away. So penetration, and temperature. So, but I'm not a super expert in this, but I can point you out to the literature.
Okay, thank you, Christian. So the last question I have here is from Christopher Monitz. So this is the question: do you have any examples of how much estimations differ between your team's approach and conventional estimation methods? And have you observed whether conventional methods tend to consistently over or underestimate?
So, yes. So, I mean, it depends on, then one really has to go into the individual studies here, right? So, but honestly, if you go to a forest or canopy cover map from Africa, or have a full continent, or they have it, you don't have there was no canopy map that takes trees, canopy outside forests into account at all, right? So therefore, I think compared to conventional approaches to quantify canopy cover, therefore, of course, indirectly biomass, there's nothing which comes close to this. Then for studies where where are we? Here, for example, here we of course directly compare to the conventional methods. So we work together with the people from the National Forest Inventory Denmark, and also other national forest inventories, and they have biomass estimations. And there we can directly compare what our method gives to what the classical methods give on the plots where we have field measurements. And there, our method is then slightly superior. So yeah, so the details you can find in this paper. But that's kind of, I mean, all these methods, of course, for example, operating on point clouds, they have always been, of course, some kind of machine learning statistics based, typically deriving spatial features from the point clouds and then doing a linear regression or random forest regression on top of it. And then we had these values available, compared this with our method, compared to the ground truth, and there you could see that our method has an edge. So the answer is yes, of course. I mean, if you wouldn't compare to the state of I mean, yes, I mean, that's, yes. It would make no point if we would not improve on the state of the art. Yes, that's our ambition.
Okay, so I think that really we can stop here. So we had a great discussion. I think this is a super cool and interesting topic. Thanks to you, Christian, for presenting and answering all these questions. It's nice that there were, I had some other questions and I didn't have time. So there were so many questions that really tells that the people is really interested about your work.
Yes.
So
I'm super happy to get questions. Also, if you have some questions, just feel free to contact me afterwards. It's my pleasure to present these works.
Okay, so thank you so much to you, Christian, and obviously all the attendees to this talk and the questions and the engagement that has been happening here. So, so thank you and have a great day.
Yes, thank you. And to my knowledge, I think there will also be an opportunity to meet on this network platform afterwards. So I will be around, and if there are some follow-up questions, I'm happy to engage there. Thank you very much again for the invitation, for having me, for the nice moderation, and for all you who watched. Thank you very much.
Thank you, Christian, and thank you all. See you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.